campus housing website, it should look fantastic. But, but I'm sorry about that. If you still need help going to Walmart or any stores to buy those, and you have difficulty to find the ride or to go there, let us know. We can help you with that. All right. But anyways, yeah. Yeah. Anyways, we hope you have a nice stay during this entire week. You feel the Southern hospitality here, and you certainly feel some of our typical summer weather patterns, I think, this week. Over there is my cell phone number. If you need anything, feel free to let me know at any point during the week. I think our conference will pretty much follow the schedule on our website. So we have, except the last day, we have a lecture in the morning, a lecture in the afternoon. After each lecture, there's a coffee break outside. I think after morning session break will contain coffee and some snacks. Afternoon, you'll see more like water, soft drinks, and things like that. There's one thing I do want to say, which is please do not bring in food or drink items except maybe water into this room. And apparently, I think this room is the advanced technology room. I think there are wires underneath the floor. And we're told that it's best not to bring in anything and spill, of course, on the floor. Water might be fine, but if possible, please do not bring in food or other drinks. All right? And that's pretty much all. So you should have your meal cards. If you are not staying on campus housing, you will not have a meal card with you, but I do have some lunch cards, only for lunch at the dining hall. If that's the case, you can come to me during the breaks. I can give you one of the lunch cards. So you can go to lunch together with everybody without having to go off campus in between lectures at least. All right, I think that's pretty much all. If there are other important announcements we have to make as they come, we'll do that maybe during the breaks or at 9 o'clock every morning. All right, so now without further ado, let me introduce Professor Gunther Uhlmann from University of Washington. And I think probably everybody knows he's the expert in the field of inverse problems for PDEs. So let's welcome him to start his lectures.
Yeah. Yeah, thank you, Chitao and Jan Rune, for organizing this and inviting me to give these talks. So it's very hard to know what the level of everyone is, so I will please ask questions if there is something you don't follow. So the first lectures will be about linear inverse problems for linear equations. So it will be elliptic and hyperbolic, like the wave equation and Laplace's equation. And then we'll go into nonlinear equations, including nonlinear acoustics, nonlinear elasticity, and at the end we'll talk about Einstein's equation. Okay, so let me start with the introduction. So in inverse problems, well, everybody probably knows about this. You want to determine the internal properties of a medium by making measurements outside. And this is a non-invasive type of method. So a prototype is X-ray tomography, which led to the development of CT scans. You have a two-dimensional section of the body. You have a source of X-rays and a detector of X-rays. And X-rays are very high-frequency electromagnetic waves. They go essentially in a straight line. This is an approximation, of course. And then you measure how much the intensity changes as you go through this, the different medium here, the different tissues in the body. And then you move the source around and the detector around, and from how the intensity changes, you try to infer what are the attenuation of these different tissues, or the density of the different tissues. So this is a two-dimensional section of the body. So this problem leads to the following mathematical problem. Can you recover a function? I will explain a little more about this. A function from its integral along lines. The line here is the direction of propagation. And this problem was solved because of completely theoretical considerations by Radon, the same person of Radon measures and Radon-Nikodym theorem. And he was motivated just for mathematical reasons, as I said before. He wanted to generalize the Func transform, which is integration over circles on the sphere. Big circles are, I'm going to talk about that a little bit later, to lines and planes. And he found a formula, which I will write down in a minute. And this formula was actually re-derived by Cormack. Cormack did not know about the work of Radon 50 years earlier in the late 60s. This was in 1917. And he and Hounsfield developed the first tomograph that led to the development of CT scans, which revolutionized medicine. They create very good images of the interior of a human body and other objects. This is a CT scan, this is a picture of the brain. So this is the mathematical problem that Radon solved. So let me do the two-dimensional case. So n is 2 here. This is the line of propagation. This is the source and detector of X-rays. And theta is the perpendicular, the direction perpendicular to the line. F is a known function, which is the different properties of the tissue, the density, or it's also called attenuation, or the different tissues have different attenuation. For instance, cancer has a much larger attenuation. And Beer's law says that along the line, x is the direction of the line here. The intensity of the detector is e to the minus the integral along the line of the function times the intensity of the source. So this is an ODE, the solution of an ODE. The derivative of the intensity is proportional with a negative sign to the density. It's a very reasonable consideration, and this is the solution of the ODE. So if you know the intensity of the detector and the intensity of the source, you know the integral of the line by taking the log. So the integral of the line is called the Radon transform in 2 dimensions. That depends on the normal to the line, theta, and the length and the distance to the origin of the line. So that's called modulo of S. S is real. So lines are parameterized. There are several ways to parameterize lines, but one way is to look at the normal to the plane, and the other, how much distance is to the origin. This is called the Radon transform. And so this is the integral of a line against the standard measure here. And he found a formula to recover from this information. Of course, this is an idealized situation. In practice, you have only finite number of measurements. From a formula, so you differentiate this, the Radon transform. There is a singular transformation. This is called principal value. I'm not going to explain it at this point, but later. So to make sense of this integral, and then you move the line around by moving the perpendicular to the line. So this you integrate in the angular variable for all angles. There is a factor here. So this is a very explicit formula, and in practice, as I said earlier, you have only finite number of measurements, and this has been implemented numerically, and it's called the filter back projection algorithm that's used in most CT scans in hospitals. Okay. So this is a very rough characterization of inverse problem that I will call this linear because, for instance, to know the integral of the function, this is a linear operation. You have two functions, you add it up, the information is the sum. So this is a linear inverse problem to recover the function from its integral along lines. And another example of linear inverse problem is called positron emission tomography, when you put a radioactive substance inside with a CT scan and you follow it. And this is the case when you have problems. And another linear problem is magnetic resonance imaging. You expose the body to a very high magnetic, very strong magnetic field. And you measure how the different tissues respond to that magnetic field. It's more or less how much water content is there in every tissue. But the ones I'm going to consider, at least the first couple of days, is the nonlinear inverse problem. One is ultrasound. So instead of taking X-rays, you send sound. This is the source of sound and the receiver of sounds. But the sound, this doesn't propagate in straight lines anymore. There is something called the index of refraction. I'm going to talk about this later also, or the sound speed of the medium. And these curves are perpendicular to the way that the waves move, the wave fronts. So it's curved in this case, and depends on the sound speed of the different tissues. So this is going to be a nonlinear inverse problem because the propagation depends on the properties of the tissues. And the one I'm going to consider first is the electrical impedance tomography, also called Calderon's problem. In this case, you apply voltages on the boundary and you measure the induced current flux. But the currents go all over the place. Here there is a very clear propagation, and X-rays is a straight line. They go all over the place. It's a very diffuse inverse problem, so it's very hard to pick up where it came from. So the information that you get at the boundary has been diffuse. And so the resolution is not as high as in other method, but however has very good contrast, as I'm going to explain. Okay, so this is the first, this is the problem I'm going to consider next. So this is again the currents. And the problem is can one determine the electrical conductivity. Electrical conductivity is the inverse of the resistivity. Tells you how much current goes from one place to the other. For instance, water is very highly conducting, blood is very highly conducting, and the conductivity will be called gamma. And then you make voltage and current measurements at the boundary. So you put electrodes around the boundary, you input a voltage and measure the induced current, or you do the opposite. You input current and measure the voltage on the boundary. This characterizes all the electrical measurements that you can make. So this is called electrical impedance tomography in the applied literature. In geophysics, it's called resistivity tomography because you are trying to recover the resistivity, which is the inverse of the conductivity. And in the mathematical literature, it's also called Calderon's problem. Calderon was a famous analyst of the 20th century. He did many important things in analysis, including singular integrals like this one. This is a singular integral that has a singularity here. And so Calderon was an engineer in the late 40s, and he worked for the oil company of Argentina. He was from Argentina. And he has also been proposed for early breast cancer detection because there is a high contrast between the conductivity of normal breast tissue and cancerous tissue. The reason for this is cancer in general needs blood to grow, and blood is very highly conducting. So again, the resolution is not so good, but you can see whether there is something very different. It's high contrast, and this can be useful as a screening method. So this is Calderon. And he says something interesting when he accepted the doctor honoris causa at the Universidad Autónoma de Madrid. He says, my work at Yacimientos Petrolíferos Fiscales, as the oil company of Argentina, still exists, was very interesting, but I was not well treated. Otherwise, I would have stayed there. So it was very fortunate for mathematics that Calderon was not well treated. Apparently, he was reading mathematics books instead of working on whatever he was assigned to. At that time, there was no mathematics degree in Argentina. The only way to get something related to mathematics was to be an engineer. Okay, so let's see. It doesn't work. This is, the movie doesn't work. And I was going to show an electric fish. You know, there are fishes that uses electrical currents to find their prey, but I cannot see it here. Sorry?
It's just slow. You have just loading.
Oh, really? No, I have experience when that happens, doesn't work. I hope the other movies work. You know, I had to shoot. Let me go back from the beginning and see what. Oh, that's why. There. See, this is an electric fish. It uses a voltage, measures the voltages to find their way around. So some food will be thrown, and then he picks it up. And this is what he's doing. See, the voltage increases. There are very interesting movies of electrical fishes in this website. So it's not just medical imaging. So the cartoon of what Calderon was thinking about is the oil is to find oil. Oil has a much higher conductivity than the surrounding rock, because again, liquids in general have much higher conductivity. So you have a log here called a well log. You put electrodes around. You input the voltage and measure the induced current flux, and you try to find oil. In fact, the Schlumberger company started using this method for finding oil, electrical method. And for
Go back to full screen.
this one?
Go back to full screen now. Full screen.
Oh, full screen, sorry. Yeah. Is that okay? Okay, so you put electrodes, you have the compressed breast here, and then you put electrodes on one side, and then you try to see whether there is a tumor. This is suggested for a screening for breast cancer, especially for younger women, because X-rays, the mammography only sends very few X-rays. And the X-rays is not so good to measure, especially in very soft tissues, the difference in contrast. But if you combine it with this type of method, then you have a much better chance of detecting. And if you detect the tumor early, the chances of recovery are very large. I know personally that mammography misses cancer, so but of course not many people have used this method. Okay, and other applications is to detect corrosion and cracks, again because conductivity changes. The seepage of groundwater pollutants, this is again the conductivity. It's very good to see contrast of conductivity. Blood has very high conductivity compared to other tissues. This is something we're going to come back later. Muscle in general is what's called anisotropic, meaning the conductivity is different in different directions. Fiber tissue is in general anisotropic. So the conductivity is much higher in the longitudinal direction than the transversal direction, more than a factor of 2. It's almost 3. Of course, in the brain is also anisotropic. Gray matter has higher conductivity than white matter. And of course, in lung, when there is blood coming in, it's much higher conductivity than when blood is going out. So this is David Isaacson, who has built some of the equipment, So this is, I think they are an ACT4 now, but this is a picture of ACT3. So you can see it's very safe. He can use it, he's using it himself. Put electrodes here. And you imagine, what you can do is imagine the blood as it leaves the heart and fills the lungs. As the pictures show here, the resolution is not high, but however, you can monitor the functioning of the lungs continuously at the bedside in a hospital, for instance. For instance, if a lung collapses, you will see it immediately here because there won't be any blood coming in. This is a movie of that situation. So the advantages of electrical impedance tomography is non-invasive. Not invasive is safe. X-rays and CT scans use radiation, so you have to be careful about how many you send, how many X-rays you're using. Portable, you can use at the bedside, can be shared 24 hours, 7 days a week. And no serious issues have been found. It's used for long periods. And this has been used to monitor the ventilation of the lung in COVID patients. The patient here has been, of course, it's not shown, but you can see the functioning of the lungs here using electrical impedance tomography because you can continuously monitor and you can move this around. A CT scan has much higher resolution or MRI, but however, you cannot put a CT scan at the bedside. You have to take the patient and so on. So this is much better way of at least detecting where there is a problem. Another application that has been trying right now is to detect what kind of stroke are you having in the brain. When you have a clot then blood doesn't go through, then you have low conductivity, and this is the image that you get from this CT scan. And when there is a burst of the blood vessels, there is a hemorrhage, it's the opposite because blood comes out. So it's high conductivity. So I said EIT is good for to detect very high contrast. The problem with this is that the symptoms of the stroke of a clot or hemorrhage are the same. So one would like to have a quick method, for instance, in an emergency ambulance, whether you're having a clot or a hemorrhage, because the treatment is the opposite in each case. So that's the potential application. And we did some theoretical work based on this, and then there are some simulations which find a number of measurements of this is high conductivity, this is low conductivity. The problem with a lot of methods, imaging methods in the brain have problems because of the skull. And this is an inclusion within an inclusion, meaning you have the skull and you have the different conductivities here. So this is the difficulty of this problem. Okay, so let me go to the mathematics. Any questions? This is just a motivation why we're going to consider the problem. So we first consider the idealized problem. You have a body in Euclidean space. You have an electrical potential U, this is the current. Gamma is the inverse of the resistivity. So the resistivity times the current is the change in the potential. That's Ohm's law. The conductivity can be isotropic, that means it's a function, or anisotropic, that's matrix value. That's the case of muscle tissue in general. And if the current has no sources or there is no sources or sinks of current, this is the divergence of the current equal to 0. So this is the first equation. I will write it here. On omega. This is great. And then you put input a voltage on the boundary. I will leave it here so you can see it, which is called F. So F is the voltage potential on the boundary, and the measurement is gamma times the normal derivative of U at the boundary. So this is the induced why can I write here? So mu is the unit outer normal. So this is the gradient of U times the normal, so how much current goes in the normal direction. Okay, and the inverse problem is very simple to state. So we consider this map, which is this, where U is a solution of this problem, which I would call a star. Okay. So the question is, can we recover knowing this map? This is like the Radon transform. I mean, the Radon transform of the integral of a function along lines, but this is very different. It's a solution of this PDE. And the problem is that this is nonlinear. So this map, you consider you want to study this map. Let me call it lambda. Okay. So this is a question of uniqueness, which is the basic question. So it's lambda gamma 1 equal to lambda gamma 2 implies gamma 1 equal to gamma 2. So that's the injectivity of this map. The stability question, and this is true for every inverse problem, is if two are close, and we have to say in what sense. This implies that the conductivities are close. Also, you want a reconstruction method or a formula like the inverse radon, like radon found for the radon transform. But this is very hard to do in general. So at least a procedure to recover gamma. Suppose you know lambda gamma, how do you find gamma? So how do you go from lambda gamma to gamma? There is a question that we know very, very little about, which is the range of this map. This is called the characterization problem. You want to know what maps can you get here that arise from conductivities. This is important because when you have finite number of measurements, you want to project through the range, so that will come from some conductivity. And there is also partial data. We'll explain that later. And so this is, but the problem in this case is that this map is nonlinear. Let me write it here. That's a huge difference with the radon transform, in the sense that you have this map here, lambda gamma is right here, but U depends on gamma here. So this depends on gamma. Actually, we don't know how it depends on gamma. That's the crux of the inverse problem. When you have a PDE, how does the solution depends on the coefficients? In partial differential equation, we are taught how to prove if you are given boundary data, how to show existence and uniqueness and stability of solutions. But we want the opposite. We know that this problem is well posed. You can solve it. How does U depends on gamma? So this is a nonlinear map. This involves derivative, and so on. So this is the crux for every inverse problem. How does the solution depends on the coefficients? Okay. So this is called the Dirichlet to Neumann map because this is Dirichlet. It's called Dirichlet data, and this is Neumann data. Okay, questions? This is the basic problem. And you consider associated to this, you consider two solutions of this problem, and this bilinear form. Let me explain. Let me erase this one, just to leave this. Questions? You have questions? Please. By the way, I plan to give notes soon. So, associated to this problem, there is something called, it's a quadratic form. How did you start again? Oh. Yeah, I got it. Which is this integral. Use a solution of this problem. use a solution of star. So this is physically is the power or the energy that you need to maintain this potential F on the boundary. There is dissipation, so you need some power, and this measure that. So this is the power needed or the energy needed to maintain F on the boundary. And you can see here the nonlinearity comes very clearly because U depends on gamma, and there is a gradient of U modulo square, so it's a very complicated nonlinearity. And associated to every quadratic form, there is a bilinear form. As indicated in this slide here, so U solves this problem, star, and G solves the corresponding problem with the G. So this is given by gamma, gradient U, gradient V. This is a bilinear form. To every quadratic form, like Q gamma, this one, there is a bilinear form associated to it. So the point of view of Calderon was to look at this quadratic form or bilinear form, they're equivalent. To look at this quadratic form here and put the problem as a PDE problem. Because in general, you want to put voltage, you are allowed to put any voltage you want as long as you don't kill the patient. And from that, try to recover gamma. But what voltages are you going to put? So the point of view of Calderon is that instead of looking at that, we look at this quadratic form because it gives you equivalent information. This is just the Green's formula, because gamma times the gradient of U solves the equation. You apply Green's formula or the divergence formula, and you get that this is represented by the Dirichlet to Neumann map here, the information that we have F, and this is surface measure. So you know this quadratic form, you know the Dirichlet to Neumann map. If you know the Dirichlet to Neumann map, you know the quadratic form. So it's equivalent information. And why is this is useful? Although it's the same, right? It's the same. But instead of looking at what boundary data to put, we are going to find in a lot of solutions of the equation, of this equation. So when you take the gradient of U squared, generates a dense set so we can recover gamma, the conductivity in the interior. So that's his point of view. So instead of looking at boundary data, you find solutions of the equation without worrying about the boundary data. So you solve the equation divergence gamma gradient U equal to 0. And the boundary data then comes after, are the boundary values of U. And those are the Fs. So we find enough solutions of the equation so that we can recover gamma inside. That's the point of view. Yes? Given any quadratic form, this is the linear operator associated with the quadratic form. Any quadratic form generates a linear operator, and that's the Dirichlet to Neumann map. Right? Yes?
Matthew, where's the power of energy Q? Is measurable?
Yes, yes, that's the measure. It's the same as the Dirichlet to Neumann map. Yeah. Of course, in practice, you only have finite number of measurables, right? Okay, and so Calderon there is you cannot solve a nonlinear problem, you linearize. That's so what Calderon did when he proposed this problem in 1980 was to linearize this map. So I want to leave this, well, I need to erase something, so I'm going to erase this. Okay, so he took the map from gamma to Q gamma. And Q gamma is here. This is a nonlinear map. We don't even know what kind of nonlinearity you have because we don't know how the U depends on gamma. But there is a nonlinearity clearly. There's modulo gradient U squared. That's nonlinear. Right? So what he did is linearize at constant conductivity, say 1, or any constant. And in this case, the equation is simply a harmonic function. The divergence of gamma, divergence of the gradient U, gamma is 1, is just Laplacian, the standard Laplacian of U. And so he linearized this problem. What does it mean? Let's call it this script Q. So he looked at Q1 plus epsilon H applied to this bilinear. Remember, there is a bilinear form here, Fg. By the way, from the bilinear form, you can see that you can recover the map, right? Because you're testing it against. Yeah, that's right. So as I said, every quadratic form has a unique linear map associated. Minus Q1 at Fg, this is what you will do when you're taking the derivative, but this is of course not, these are the spaces of function divided by epsilon. So epsilon goes to 0. So you take a direction h, this is 1 plus epsilon h, and you take how much does this map changes in this direction. It's called the Frechet derivative. It doesn't matter. He looked at that map. And then this is an exercise. I'm not going to do this calculation, but you can show that this map gives you, is indicated here, is equal to this. So this h is the direction of the derivative. It's like the directional derivative when you take a function of several variables. But this, of course, is this function space is a little bit different. Gradient u dot gradient v. So this is what we know when you linearize this map, where u and v are harmonic functions. These are Laplacian equal to 0, u at the boundary is f, and v at the boundary is g. Okay, so the question is whether we want to recover h. So the linearized problem is to recover h. Now this is linear because it depends on h. This is linear in h. Right? U and v are just harmonic functions that we can choose. We have a lot of freedom. This is, again, the point of view of Calderon, is to find solutions of this. enough solutions so that the product of gradient U to gradient B is dense. And he took very simple solutions, which are going to be the key for us. He took e to the x rho and b to be e to the minus x rho conjugate, where rho, I will come back to this, rho dot rho is equal to 0. So let me explain this in a little bit more detail. Because this is the key to the solution of the inverse problem. So rho in Cn means rho has components, rho 1, rho n, where the rho i's are, can you see? It's over there. I thought, oh, rho the rho, oh, you cannot see that, oh, sorry. Where can you see up to here? Approximately. Okay, so I will repeat. Rho 1, rho I are complex numbers. So why rho dot e to the x rho means is e to the x dot eta times e to the I x dot c, where rho is eta plus ic, and eta and c are vectors in Rn. This is a complex vector. And rho dot rho equal to 0 because the Laplacian of e to the x dot rho is rho dot rho times e to the x dot rho, right? So if this is 0, this is 0. That's why you need the condition rho dot rho is equal to 0. So what does it mean rho dot rho is equal to 0? It means it's easy to check. So I will write it here. After, so I'm going to just leave this. Rho dot rho is equal to 0 is equivalent. You just do the rho 1 squared plus rho n squared equal to 0. This is not the modulus, right? They're complex vectors. And this is equivalent to the length of the real part equal to the length of the imaginary part and perpendicular to each other. So for instance, in 2 dimensions, you have eta and you have c. These two vectors, they have to have the same length, and they have to be perpendicular. In 3 dimensions, we have more options. You take a vector eta, you can take c to be the combination of these two vectors. Right? You need the same modulus, of theta. So it's a circle, or radius, the modulus of this perpendicular to it. So this, what happened here? Can I move it here? I'm going to explain this in detail because it's crucial for the rest. Okay, so in dimension 3, so in dimension 2, you have only two vectors. So you have a vector c. There is this possibility or that possibility. The length has to be the same. right? I put eta, sorry. So C is either this vector or that vector with the same length. In dimension 3, you have eta, then you take the circle of the same radius, and this is perpendicular. So you intersect the sphere, this will have radius modulo C, and this is perpendicular to that. So there are many more vectors, right? There are all these vectors perpendicular to eta in the plane, perpendicular to eta, and then you take the same modulus. Okay, so the higher the dimension, the more vectors that you have. So Calderon, I'll finish with this. Maybe I will erase this because I have this identity here. So this is actually going to be important. Then he took U to be as indicated here. Oops. I need to do it every time. So this is the problem. And this is what he took. And substitute in here. E to the x rho, and B to be e to the minus x rho conjugate. So rho is eta plus IC. Eta minus IC, I guess I put here. It's a minus sign. Over 2, these are two perpendicular, they have the same length. And then if you do this operation, you get C squared. This is an exercise, e to the I. The real part cancels out because I took minus rho conjugate. So rho is this, and minus rho conjugate, let me write it here, is equal to minus eta minus IC divided by 2. So the real parts cancel out, and you get e to the minus I x dot c h dx. So that's the Fourier transform of the characteristic function of omega and c. You know this for every c, so you know it for c non-zero, and that's enough to recover h. The Fourier transform of an L2 function, from that you can recover a function if you know it except in a set of measure 0. So this is only a c equal to 0, you don't get it. So you can recover the Fourier transform of h in the domain omega. So h on omega. So it's very simple calculation, but this is the point of view. The main point of view is to find solutions of the equations. And this is, I'm going slower than I thought I would go, but is it clear? And I know some of you already, but a lot of you I don't know. Is it make sense?
What is function chi here?
The characteristic function of omega. The characteristic is 1 in omega and 0, because this is integration over omega. So here this is 1 in omega and 0 outside omega. Again, I assume that you know about the Fourier transform. Here is one of these conditions. Okay, so in the afternoon I will talk about the nonlinear map. This is the linearized, doesn't imply anything by itself. But this is in finite dimensions, you have the implicit functions theorem that tells you can solve the linearized problem, you can solve the nonlinear problem locally. But that's not true for infinite dimensions. This is spaces of infinite dimensions. You need to know more about the range, for instance. So we don't know. And therefore, you have to do something different. But however, although it does not imply anything by itself, the idea of taking these type of solutions turned out to be very important for the nonlinear problem. Okay. So I will continue in the afternoon. Yes.
Linearize around the non-constant.
Yes. This doesn't work. Yes, so this is it's a good question. The method that I will explain will actually imply that. So the question was, any questions about this? The question was, this is really great. Even I can use it. All the classrooms have this? All the classrooms have this type of... During the pandemic, I had so much trouble, with writing. And okay, Jan Rock was asking the question of what happens linearize. It's a good question. Linearize not at gamma equal to gamma 0, not necessarily 1. And then in that case, you cannot take this solution because this is the divergence. We have to take this, gradient u equal to 0. And now if you linearize, there is the quadratic form and the bilinear form also, which is the same as we had before, except that these are solutions of this equation. Now, then we need to solve this equation, and the linearized problem is the same. You linearize in the direction h, you will get h gradient u, the gradient v. You will know this for u and v solutions of this equation. So the divergence also v solves this equation, right? The bilinear form associated with the quadratic form. But how do you solve this? So that's the question. And this is the same question for the nonlinear problem. So I want to solve directly the nonlinear. So we don't know how to solve the linearized problem yet, but we are going to see it right. Okay. Any other question? This is not a lecture. No, this is a lecture, but not. We can interact, right? It's not like a conference.
As the estimates, when you recover H.
Yes.
So, as the estimates between this recovery and the solution to nonlinear problems, how big is the CDO?
Yeah, that's. No, we don't know that because the linearized problem does not approximate the nonlinear problem in infinite dimensions in general. You have to know something about the range. But you can always try this. This gives you an idea of what to do. In some problems, the linearization is good enough. And we're going to talk about that later, actually, but not for this one. This, for instance, Calderon's solution does not imply that the nonlinear problem is solvable close to constant. Suppose you are a priori, this is your question, suppose you are a priori close to constant, can we solve the problem? No, not with this method, not yet. Okay. Actually, I'm running late. But there is no rush. Huh? Okay. Any other question?
Can you think with general phase function?
Yes, we are going to see more general phase functions.
Because here you invert like a Fourier transform and you say, what if I want to invert a FIO?
Yes.
You do it directly?
Yes, we are going to see more general phase function, but how general is That's the question. Because we're going to, actually, since you're asking, let me show you other solutions. Uh, these are going to be other solutions here. So this is more general phase function, phi and psi. But you still need that the gradient of phi is perpendicular to the gradient of psi. And the modulus of the gradient of the real part is the same thing as we had for the, and this is a system. We're going to talk about this. It's a system, and it's not possible to solve in more generally, except in dimension 2. In dimension 2, we have a lot of solutions. And we're going to explain this. This is it's called the Conal equation, and I want to talk about this later. There are more, but not enough to solve every problem. Any other question? Please don't be shy. I'm not going to bite. Okay. So what does it mean, discussion period? So I have asked some of my some people to give talks, but not right now, but some of the discussion.
Do you have any specific plan for the discussion here? So I would just encourage you guys to maybe talk to each other. If you have any other questions, you may ask Gunther students and postdocs will be here to help.
But some of them will.
Any exercises that you can
Okay, I can give you an exercise. Yeah, no, there is a very. I'm going the other way. No, I'm going the other way. Sorry. There is an exercise already. We show this linearization. It's not complicated. You cannot solve it, we can try to do it. Yeah. Go ahead. Try to do this. Or in general, compute the linearization. For any, the question you were asking, for any, we can solve it in the case of one, but this is actually the answer in general, where U and B are solutions of the equation with data F on the boundary for U and data G, the boundary for V. And the case A equal to 1 is just the Laplacian, which is, this is the linearized problem. Even though does not imply theoretically anything for the nonlinear problem, you can always try it. And there are papers on this, looking at the linearized problem. The fact that you cannot prove something doesn't mean you cannot do something about it.
Could you say a bit more? What do we know about this integral, which is in green gray?
Okay, from this integral, that means we can recover, we know this quantity for every U and V harmonic, for every. So we have, we have a lot of solutions. That's the advantage of Laplacian. So this is what we're going to try to do in general. We are going to have something like this, not exactly this, because we're not going to linearize anymore. We're going to try to find enough solutions so the products of the gradients or the product of solutions in general is dense. That's the key issue for the inverse problem.
And probably on the boundary, U and V are equal to 0, right?
In this case, H does not need to be 0, but for the nonlinear problem, we have to have something at the boundary. I will explain that. Actually, this is the boundary determination. Yes.
I was just curious, that quadratic function,
Yeah.
is it true if you minimize that function, you will be solving
Yeah.
that equation over there?
Yeah. That's another way to show that there are solutions of the equation. You minimize this integral, gamma gradient u squared, over all functions with value f on the bound, that have all sufficiently regular functions that have is h1, that have the value f on the boundary. And that gives you solution of the Dirichlet problem. That's another way. There are many ways to solve the Dirichlet problem. That's one. You take this quadratic form. For every u, not just solution of the, you're trying to find the solution of the equation. And then you minimize overall functions sufficiently regular that have the value f on the boundary. And that gives you solution of the elliptic equation. You have to show, it's not trivial because you have to show that the minimum is attained. That's the key difficulty. Any other question? There are many ways to solve this problem here. There is, probability way. You can use probability, exit time, or Brownian motion, or other processes to solve potential theory. Just to name a few, there is a pseudo-differential operator way to do it, more general. There are many ways to solve. There is a general theorem, meta-theorem here. The easier is to solve the direct problem. This is called direct problem. Given f, find a solution. The more difficult the inverse problem is. So for hyperbolic equations, it's harder to solve the direct problem. But the inverse problem is easier than for elliptic equations. In general, this is I cannot claim a proof of this. This is a general statement based on experience.
I'll ask a question. So what if you don't know the Dirichlet lemma? You only know like finite many.
Right. Well, the idea for this is like in the Radon transform, right? We want to solve the problem and then discretize, right? But first we need to solve the idealized problem. Like that's why I gave this as a model. This Radon transform this is also the same issue, right? We cannot send an infinite number of X-rays. So, but here you have a formula. So the filter-back projection, there is an algorithm based on this. So you discretize, you have only finite number of measurements, you discretize the integral, you discretize this. It's not trivial. I mean, there is a whole book of natural mathematics or computerized tomography dedicated to the algorithm, to developing the algorithm. So that's the idea. It's not to take directly finite number of measurements and then see what you get, but solve the idealized problem and then discretize. That's the general method proposed here. So for this problem, there are numerical methods, and I will mention it later. There are numerical methods. So, yeah, who was?
I was just wondering how people tried, this I guess only for mathematical, people tried doing this on unbounded domains.
Yes, there's some work on unbounded domains, on the Slav, for instance. Yes, there has been some work, not in every unbounded domain, but Some
Jesse Rilo.
who?
So I think Jesse Rilo. Did he work on these scripts?
Who?
Jesse
This is Railo. Yeah. Yeah, but there are many other people that work on this. It's a Slav, called a Slav. A half space. You can. But the special, not for every unbounded domain. This is what I'm doing now is for every bounded domain. Smooth enough boundary. I haven't talked about that technical aspects, but yeah, that's a good question. It's also related to waveguides. Instead of this equation, you can consider the Helmholtz equation, Laplacian plus k squared, and that's related to wave propagation. So, any other question? Okay.
That linearization identity is pretty trivial. You just use the linearity of the interval and the epsilon will cancel.
Well, come here and do it. See, this is the discussion period.
Or maybe we can have a break first.
Okay, well, let's have a break.
Grab a coffee or a
And,
snack.
and then discussion, you do it.
During the discussion, you'll be solving that.
Okay. That's it.
Thank you.
Sure. Okay.
Again, just make sure do not bring in food or drinks other than water. Thank you. You cannot bring.
thank you.